System protection. System protection is power system protection. Power system protection, there's so many protections for the electrical power system. The only one that we're going to talk about the system protection, Chris, today is overcurrent protection system. Overcurrent. Actually, when you go into the high voltage, you start doing over-under frequency protection. Nick, you will do over-under voltage, directional overcurrent protection device coordination. So tons and tons of protection. Today, our focus is protecting the electrical equipment from overcurrent. Can I have a thumbs up, Chad? We understand. We care less at this point about the frequency because the frequency on the low voltage, guys, is not an issue. For the most part, the frequency is constant by the utilities. The voltage, for the most part, is constant. You can correct it with power factor, correction medium, directional overcurrent protection device coordination. Not an issue in the low voltage. It becomes an issue in the high voltage. So focus on overcurrent protection device, guys. That's what we're going to do. So devices to protect the systems, Chris. Our focus is on overcurrent protection devices. Hold on, we're going to Jackson, my friend, this is a fancy name for a fuse or a circuit breaker. Cool. So we're going to protect the system from overcurrent. Forget the voltage, forget the frequency. We assume they're good. The only focus here is overcurrent protection device. A few things. Overcurrent protection device, like I said, guys, you have a circuit breaker, and also you have a special type of a circuit breaker or a function in the circuit breaker that's called ground fault protection device. Circuit breakers or fuses, guys. There's fuses, circuit breakers, and ground fault protection. I'll explain what a ground fault protection in a second here and how they operate and so forth. Now you're big boys. You no longer are allowed when you graduate from here. You no longer remember that how many times I told you to go to 240.6. If you go back to my YouTube presentation, every single one of them, when we sized the overcurrent protection device, where did we go? To 240.6. Today we're going to go to 240.6. We always go to 240.6a. We rarely, if ever, mention to go to 240.6b. I don't know how many of you guys have been there. Now we're going to go to 240.6b. And no longer, all these nice standard, Chris, overcurrent protection devices right here, they become meaningless when you go higher than 1,000 amp because everything is adjustable. So that's very, very important concept. So that the concept of adjusting devices, overcurrent protection devices, guys, the overcurrent element is a big, big deal. You have a 2,000 amp circuit breaker. Guess what? You can make this 2,000 amp circuit breaker at a 200 amps. And when you trip it, adjust it to 200, guess what? The 2,000 amp circuit breaker now is treated as a 200 amp circuit breaker. Who cares? The question, tell my friend, is who cares? Well, when you size your conductor now, yes, you're tying it to a 2,000 amp circuit breaker. No, you're not sizing the conductor's 2,000 amp. You're sizing it 200 amps. That's kind of a weird. So we're going to be sized based on the trip. Big, big deal. Selective coordination, guys. I just talked to our friends at SKM, and we received all the site code for you except for 2 of you. I will be installing SKM on your machines. This will lead us directly into the software that we're going to be doing. It's called Selective Overcurrent Protection Device Coordination. Fancy name for if you have a short circuit in this light above Tao's head right here. This is a 20 amp circuit. If I have a short circuit or a ground fault on that one, do you really want the 3,000 amp fuse done with his service to trip? Would that be cool? Or for you guys probably would cancel the class. I'll be cool. So you don't want the 3,000 amp circuit breaker to trip. You would hope the 200 amp circuit breaker in this sub panel will trip. So that's what the overcurrent protection coordination. Big, big, big deal. I want you guys, so we have the overcurrent protection device. So for the overcurrent protection device, guys, we have either a circuit breaker or we're going to have a fuse, as you guys have seen all the time, the fuse or circuit breakers. Fuses and circuit breakers. Here's a fuse. Chris, every time you have a fuse, you always have a disconnect with the fuse because the fuse cannot be used as a disconnect for the most part. You have to be able to isolate it. So these are the 2 devices that we're going to have, either a fuse disconnect or a circuit breaker. There's another device, guys, they also use, they're called the ground fault protection. The ground fault protection, guys, it's required. Let me just tell you where the code is because I know you all care about the code, right? Say yes, Chad.
Yes, Chad.
Yes, okay. So the overcurrent protection device, guys, on the service 230.90, this will get you to 230.95. If you go to 230.95, this article talks about the service. It will tell you, here's what it tells you. If your voltage, if your amp is 1,000 amp, the circuit breaker is 1,000 amp, Chris, 1,000 amp or higher, or higher, or higher, cool. The voltage is 480, 277, 480, Chad, not 430, 480, 277, 1,000 amp or higher. You are required to provide a sensor that's called ground fault protection to protect the system from ground fault. Now, Rob, on a system 1,000 amp or higher at this voltage, guys, 1,000 amp or higher at this voltage, the circuit breaker itself cannot see a ground fault. It will see the ground fault as a load. It wouldn't trip fast enough, Chris. It wouldn't trip fast enough. So the smarter than Chad, what they do, guys, they have a sensor here that senses the ground fault and sends a signal to the circuit breaker to trip. That sensor is only looking at the ground fault. Anything on the ground fault, it will looking specified for the ground fault. So remember, you're going to put this one on a service, required by the service. And also, let's go put it on the feeder. And write these guys because they're really cool when you reference to them. If you go to 215,
is the sensor tied to each phase?
The sensor actually looks at each phase and the neutral, looks at the current that's coming from each phase and the neutral, and if there's a difference between each phase and neutral, substantial difference, this means you have a ground fault because one current is going through the ground. So very sensitive. It looks at the current that's coming into each phase, the current that's coming out the neutral, the balance. So they have to balance, right? Either balanced or it has to be equal. What comes in, either balanced or equal to what's coming out. If not, some of this current went right through the ground and it trips. It sends a signal to trip or alarm. By code, guys, if you go to 230.95, you're going to see the 1,000 amp or higher. The voltage has to be 150, more than 150 to ground, but less than 300, and it's required on the service as well as the feeders. So Ashley, when you go to the feeders also, they're required. Where do they put them in the feeders? On 215.10. Yep, ground fault, 215.10. So if you guys go to also 215.10, it will tell you this is also required on a feeder. Everybody knows the difference between service entrance disconnect means and a disconnect means or a circuit breaker for a feeder. So take this. If this was here's a feeder here, and if I have another, say, let's just say this one for practical reasons was 4,000 amp, and this one a 2,000 amp. So Chris, do you agree with me, my friend, that this is a service overcurrent protection device, right? The top one, the service. Yeah. Do you guys agree with me that this one is a feeder overcurrent protection device? So now I need one here, one ground fault on here, and one also on the feeder. On every feeder, not just the feeder. So if I have another feeder right here, also 1,000 amp, what do you need? You need another one. On every feeder, 1,000 amp or higher, you need, or a service, you need a ground fault protection. Why? Because at that amp, the circuit breaker guys cannot trip fast enough on a ground fault. So they need a sensor that only looks at the ground fault. Okay? Here's how they define it, guys, by solid. Of course, it has to be solidly grounded, because if it's not solidly grounded, you don't have a neutral, right? So if you solidly grounded, blah, 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 if you guys read through all this description, you're going to end up with only required on 2 voltages in the US. On a voltage of 480/277 and 600/3. What's the 600, guys, divided by square root 3? I don't use this one. So if you take 600 divided by 1.73, that will give you 347. 347 volt. Not commonly used, the Canadian voltage here. Okay, on these voltages must, if you have any of these 2 voltages system in your building, and not or, Chris, and your service or your feeder is 1,000 amp or higher, you must have a ground fault protection. If you don't, it's recommended. So here's my question for, whom am I going to pick on? Tao, is it required in a 208/120 volt? Is it required on 208/120? The ground fault.
No.
No, it's not required. Why? Because it's only required on the voltage to ground. Look at the voltage to ground is 150 or higher. 150 or higher, right? If your voltage is 150 or higher. So it's not required on 28120 system. These are baby system. 28120 three-phase is baby. 24120 baby system. Cool? So these are not required. If you have 240/120, single phase or three-phase, not required. Can I guys get you to understand it's only required on these two systems? Can I have thumbs up on that? Anybody knows why? At a higher voltage and higher amps, what do you get? You get higher energy if you have a ground fault and more destructive ground fault. At a lower voltage or lower amp, obviously you get lower destructive energy. So it's not as essential in a 28120 system, the ground fault, as essential as in a 48277. So please write these things, guys, when you go to the ground fault. We'll look at the setting in a second. Recommended, guys. Recommended, it's required on feeders. That was required on feeders. Also recommended on branch circuits. If you have a branch circuit that meets that criteria, it's recommended. Also recommended on less than 1,000 amp. In hospitals, if you ever worked in hospitals, my sister is online now. If you ever worked in hospitals, guys, in a hospital, they require you to have two ground fault protection. One on the service and one anywhere else downstream. So if you have 225 amp panel in a hospital, fed from 1,000 amp circuit breaker, you have to have one in the 225 amp and one in the 1,000 amp. On a hospital, two ground fault protection. So they recommended it for even less than 1,000 amp. Exception, if on the feeders, guys, on the feeders, they have an exception. If you have a process and that process is mixing chemicals, and if you interrupt that mixer of chemicals or nukes, say you interrupted it by ground fault, you got a ground fault in the system and you trip and you interrupted that process, you're going to create more hazard than burning a conductor. You basically going to blow up the building. So if you have a process that mostly industrial, high-level industrial, guys, chemicals and so forth, you're excused from having ground fault in them. Why? Because interrupting the service will create more hazard, more explosions than burning a circuit breaker because of ground fault. So that's just a little exception on that system. Any question, guys, about the requirement of ground fault? Ground fault, we'll talk about it in a second, guys. Selective OverCurrent coordination. Here's the light right above you. This is my light. It's the system as here is 277 volt. So we sent Ashley to go maintain this light, and she changed the ballast here, and she shorted the 277 to the ground, right? Could it happen? I could short it to the ground. Do you guys want the main to trip or this one to trip? Which one do you want to trip? You want this 20 amp circuit breaker to trip, not the main. That's called the overcurrent protection coordination. The closest to the short will take care of the problem, right? So if this did not trip, this is your line of defense. I call it line of defense. Line of defense number one is right in here, this circuit breaker. Well, this malfunction, right? So the second line of defense is the fuse here. Well, this fuse happened to malfunction again, did not trip. Your third line of defense would be what? The main circuit breaker will trip, shut you down. If that doesn't work, guess what? The transformer also have a fuse on the primary, the 13.8K. There's a fuse here. This is your fourth line of defense, but by the time this trips, the fire department will be inside your building fighting the fire. So it really doesn't matter if it trips at that time or not. But the Excel, see where the last line of defense, right there. You short your building. Do you think they want your building to take down the transmission line? Of course not. Or the distribution line? No. They will allow your building to burn to save other buildings. Can you guys see how you start with the short circuit here in the light above you? The panel, now then the panel here, all the way to the service. And if all of them fail to operate, then the fuse on the primary of the circuit breaker will operate. And oh, by the way, what happens if that fuse fails to operate? There's also fuses here. There's so many protection and relays downstream, upstream. Any question, guys, about this? Overcurrent tissue coordination. This is what you're going to be doing, guys, with Chad, SKM, starting tomorrow. We're going to walk you through the software, so you're going to learn about it. Okay, Chris, ground fault. Here's how the ground fault works. You have a circuit breaker. This is a 2000 amp circuit breaker. It's a 480 volt slash 277 volts, right? Is it required? Yup, because it's more than 1000 and the voltage is 48277. So, okay, so this one is the three-phase. This will take care of the three-phase. This big boy will take care of the three-phase short circuit. Three-phase short circuit, that big fat boy will take care of it. If you have a ground fault, they have a sensor, a donut like this. And can you guys see the current that's going through each one of these phases and the current that's going through the neutral? If they have a balanced system, the neutral will be carrying 0. If the system is not balanced, you're going to have a current through the neutral. So this will look at the current in every phase and the current in the neutral. Analyze them, and if there's substantial difference between them, this means that phase is actually shorted to the ground. Right? Any one of them. If the current goes to the ground, you will alter the current arrangement in this donut. Long story short, you'll be able to sense there is a difference between the current coming in, the current coming out on the neutral if it's unbalanced. Because there's some current went through the ground now. That guy, all what it needs is just sense that there's a current. After that, it's in the signal here, a little I signal here to the circuit breaker. There's a little coil, guys, little coil right here, little coil right in here. It sends the signal, closes the contact, energizes this coil, tiny little coil that comes with the circuit breaker, and bam, the circuit breaker will trip. Who cares? It trips fast on a ground fault. It looks on a ground. If you don't put this arrangement, and you depend on the circuit breaker to see it, it will see it, but not fast enough before the conductors start melting and creating fire. Yes, Rob? They have different technologies, guys, that they do it. One technology is one donut per 1, 2, 3, 4, right here. Exactly what you just said. They lube them up and they bring them in. That will sense the current in each and every one of them. Another technology is to have the current sensor on all of them. Chris, this big fat thing that you're looking at, the current transformer, this all could be part of the circuit breaker, guys. This is all built into the circuit breaker. It could be built into the circuit breaker 99% of the time, or it could be standalone system. Any question, guys, about the ground fault? So it senses what's going on in the ground and will alarm you. Why? Because a circuit breaker by itself cannot sense fast enough a ground fault. Ground fault on a 4,000 amp. Take this. A ground fault in the 4,000 amp switchgear can be 200 amps. So as far as the 4,000 amp circuit breaker, it's we're having fun here. We have 200 amps. That's a load, right? That's why when you have a ground fault, a low ground fault on a 4,000 amp switchgear, that's say 1,000 amp ground fault on a 4,000 amp switchgear circuit breaker, it's still load. 3,000 amp is still load. All the way to 4,000 amp ground fault, that's still seen as load. But by this big fat thing here, you have to have a special sensor that looks at the difference between the phases to identify it as, I guess it's more scrutiny. They scrutinize it to identify exactly as a ground fault so you can trip. Any question, guys, about this? So that's a new concept, the ground fault. You're going to see it on the coordination that we're going to be doing. Okay, the second part of so we'll get into the coordination, guys. So we talked about the ground fault, we talked about circuit breakers. The second part of this chapter talks about circuit breaker types. You guys are familiar with these type of circuit breakers, right? These ones are called molded case circuit breakers, air circuit breakers. If you open any one of them, Dustin, would you find oil? I hope not. Would you find a vacuum tube there? Not really. So circuit breakers, guys, based on the construction, the way they construct them. construction, the way they construct them, guys, are divided into three types. Based on construction, they divide them in three types. Type number one, the most common one, is the air. This is number one. Almost, I would say 95% of the circuit breaker that you guys are going to handle in your career are called the air circuit breakers. 95%. Did you guys hear me? 95%. These are mostly air, mostly 600 volt or less. So Chris, any circuit breaker, 600 volt or less, 99% of the time, you're dealing with what? Air circuit breakers. No question asked. So now you can sleep on the other two. The second one is oil circuit breaker. Oil circuit breaker, as the name implies, guys, when they interrupt in a tube that's full of oil. That's all. They have a tank full of oil, and we have a short circuit. When they interrupt the short circuit, they interrupt it. The contacts are immersed in oil. Anybody can tell why they put it in oil? Oil will extinguish the arc. A huge arc will come out of it, and the oil basically will kill the arc. So write to yourself a note. This is a medium voltage, guys. This is 5 kV, 15 kV, 25 kV, and so forth. So that now you're talking about high voltage system. And also vacuum tubes, for the most part, vacuum tubes, they have a tube, and they remove all the air from the tube, and they put the contacts inside the tube. You're going to look at them, guys. And if there's a short circuit, he will interrupt the short circuit in a tube that has no air on it. Anybody knows why no air? If you have an air, every time, guys, you interrupt a 4,000 amp in air, the amount of energy that you're interrupting will ionize the air and make the air conductive. So momentarily, the air will become conductive, and you have a big arc coming out of your contacts. Big arc coming out of your contacts. Who cares? Over time, you will destroy your contacts. They will no longer work. So the smarter than Chad, the higher the voltage, the more severe the arc is. So what they do is, in a vacuum, if you don't have air, then you're going to, for the most part, not completely empty. If you don't have air, what are you going to ionize? There's nothing. It's vacuum. So you ionize nothing. So basically, you can extinguish the air, the arc faster. There will be no arc or very small amount of arc coming out of the interruption.
Why are vacuums not used?
It's not economically visible to use it. It becomes economically visible to use in a high voltage because the arc becomes very severe, extremely severe. In a low voltage, there are other technologies available that can handle the problem in the low voltage, much cheaper than the vacuum tubes. Okay, so that's these. Any questions, guys, about the way they construct it? The air, oil, or vacuum? Air, oil, or vacuum. So for most of us, guys, we're talking about air, and that has to do with interrupting the way they build them and how do you interrupt the arc. Do you interrupt the arc in the air? It's an air circuit breaker, like these. Do you interrupt the arc in oil? The contacts are immersed in oil. It's an oil circuit breaker. They use them in the switch yards. Do you interrupt the arc in a tube that has no air in it? Vacuum? Then it's a vacuum circuit breaker. Different technology. As you can see, guys, the more you go from 1 to 2 to 3, so this will be my 2, this will be my 3, the more expensive the equipment becomes, and the more to a higher voltage and higher amps the equipment will be rated. Okay. Any question, guys, about this construction before we move on? Any question about this? Yes, sir.
Utility use oil or vacuum?
They use both, oil and vacuum. A lot of 515, 25 kV. The higher the voltage, the more they start to use vacuum tubes. A lot of vacuum tubes becomes, and then they have gases that they treat, tons of other things that they can add. Any questions, guys, about these three technologies of construction? Okay, cool. So let's go to the, then there's two technologies. So that's the technologies of how they build them, how they extinguish the arc. There's also two technologies, guys, based on how do they sense the current and how do they trap. The cheapest piece of equipment you can buy, circuit breaker, is the one on the wall. It's called thermal circuit breakers. That thermal circuit breaker, guys, since it's a heat, it has a heater. You'll look at it in a second. It heats bimetallic strip. That bimetallic strip heats. When it heats, it expands and pushes a contact, open a contact basically, to open the circuit. That's called thermal circuit. And there's some delay that you can put in it for, for a couple of like circuit breakers, for inrush on motors and so forth, based on the design. It's like the overcurrent protection device. This is exactly like the overcurrent protection device. Take this. So if this is my load, guys, and I have a circuit breaker. This circuit breaker is at 20 amp, right? Now, if I pull out of this system 30 amp, right? This is rated 20 amp thermal circuit breaker, and I'm pulling 30 amp. I'm overloading it. So this 30 amp, guys, is going to go through where? Through all this heater. What's going to happen if you put a current more than the heater? The heater is rated not to trip up to 20 amp. You put higher than 20 amp, start heating more, creating more heat, more heat, more heat, more heat. And guess what? After a while, this will expand, push this way, and it will open the contacts, right? Can you guys see these contacts? When it heats this bimetallic strip, and that will push the contacts, these contacts, push them to the other side, open the circuit breaker. That's the overload. That's exactly like an overload, guys. Almost exactly like an overload. So, what happens if you have a short circuit on this? That can't see it. That cannot see it fast enough. This is only handling overload. Overload condition. Any question, guys, about the thermal circuit breakers?
Will they melt back? Will they come back?
Yeah, oh yeah, they will cool down then. Yeah, after it cools down, it closes. But it takes time. If you go to a circuit breaker, guys, and it keeps tripping, if you try to reset the circuit breaker, it wouldn't reset. It would take a thermal. They need some time, a couple of minutes, maybe 20 minutes, 10, 20 minutes to cool down so it can close. Like overload. Overload is very similar.
So that's mainly an air type circuit breaker.
We're talking about air here.
Okay.
Everything that we're going to talk right now is air. These are air.
And would these circuit breakers generally be for motors?
You can use it for feeders, for any application. Yeah. It's not, this technology, Chris, is not reliable for overload for motors only. Motors, guys, because they're so special, we have this circuit breaker to protect it from overload and a separate device that also look at the overload.
Okay. So where does it say on a circuit breaker? I think Chris said a few times, like when we talk about receptacles, how do we know that it's the bimetal strip?
If it's thermomagnetic, most of these thermomagnetic,
yeah,
we really don't care with the technology, bimetallic or whatever. What you care about is you have, if it's a thermal, there's something inside that heats and trips.
okay.
So that's so this is the symbol that they can use. Can you guys, does that feel, this is the overload symbol they use. Here's a circuit breaker of a type of an overload. This is circuit breaker of an overload. This is thermal circuit breaker. So it's a circuit breaker that only works on thermal. That's the only similar thing to it, guys, is the overload that we use in motors. Okay. Now, the other component is called, so that's thermal circuit breakers. The other component is magnetic circuit breakers. The magnetic circuit breakers, guys, you look at them, they're looking, what they do is they have a coil and they put it in series with the load. A coil in series with the load. The code give them the name instantaneous circuit breaker. Remember that term instantaneous circuit breaker that we use for motors? All what they're looking at, short circuit. They're looking at what? Short circuit. If you have one of these on a feeder, the feeder can burn because of overload and they're still sleeping there. They're looking at short circuit. Do you short them to phase or ground? They wake up. They don't short them, they wouldn't wake up. So they're looking at short circuit. Then they have the one, the notoriously famous that you guys all know and probably you're going to spend the rest of your career dealing with, thermomagnetic circuit breaker. Thermomagnetic circuit breaker, my friends, you're looking at them right here. it has two technologies, one thermal and one magnetic. Why? Thermal for overload and magnetic for what? Short circuit and ground fault. You're done. Ground fault. So they put the two technologies together, they make a thermomagnetic circuit breakers. Okay, here's the instantaneous strip circuit breaker, guys. The magnetic circuit breaker, they call it. What they do is they have, so you have, Ashley, we sent her to work somewhere, and she did short this system to ground. Take this, I have a short circuit. Now, out of inside, this is a 20 amp circuit breaker, the same 20 amp circuit breaker that we looked at. Now I have a ground fault of 1000 amp. I have a ground fault of 1000 amp, right? I shorted phase A to the ground. Okay, now this 1000 amp will create what? A magnetic field, very high magnetic field. There's a coil, magnetic field. The magnetic field, guys, like actuators, will create a force. That force, because it's magnetic field, momentarily, you're putting huge amount of current to a coil. And inside it, there's a plunger that moves. So you create a force. That force will push these contacts right here. Can you see that? It pushes these contacts that tie to it. That will push these contacts to open. It will push these contacts to open. Based on the high current, they're creating a magnetic field, that creating a force, physical mechanical force, that push the contacts apart. Through the solenoid arm, removable contacts, stationary contacts, these are where the current, the 1000 amp is coming, right? Oops, it's going to be right in here. Well, yeah, it will be 1000 amp here too. So it's looking at a ground fault and short circuit. This is what we call an instantaneous third circuit breaker. The ones that you size based on 8 times for motors, guys. 8 times. Chris, this is how they do it. Circuit breaker. This is instantaneous circuit breakers or magnetic circuit breakers. Obviously, you don't use this often. Cutler hammer, guys, call this is motor protector. Motor protector or something like this. Motor protector. So a lot of manufacturers, guys, you know what they do? A lot of manufacturers, they have this type of circuit breakers with a specially designed overload and a contactor. Where we're going to put the contactor down here, and a contactor, and they make a starter. This is commonly used instantaneous strip circuit breaker. Why? Because this instantaneous with this overload tied to a motor, that's exactly, you put an overload with an instantaneous, together they act as what? They're going to act as a thermomagnetic circuit breaker. So just be aware of that one. This is the one that you guys love all the time. You're going to live and die with. It's called thermomagnetic circuit breakers. That's the one that we do all the time. We don't show this when we draw. We just saw a circuit breaker. I want you to, this component is the overload component, and this component is short circuit and ground fault. And these are your thermomagnetic circuit breakers. Thermomagnetic circuit breakers. You can buy them probably up to 1600 amps. Up to 1600 amps. After that, it becomes electronic circuit breakers. Electronic circuit breakers. Any question, guys, about this? Thermomagnetic circuit breakers. Your thermomagnetic circuit breakers. Before I leave this one, guys, now this is the technology, the old technology. The new technology is called electronic circuit breakers. What they do, and I'm not going to, they have a circuit breaker, guys, they have a sensors inside it. That's exactly what they do. A sensor that senses, I'm just showing phase, this is one line diagram. This is electronic circuit breakers. Electronic circuit breakers, they're air. Electronic circuit breakers, you know what they do, guys? Instead of the thermal and the magnetic, they use a sensor that senses the current in phase A, phase B, phase C, and a neutral. And if the current goes higher than a predetermined value, electronically send the signal to trip the circuit breaker. And on a ground fault, on an overload, and a short circuit. These are your so-called electronic circuit breakers. This becomes a big deal, guys. You can buy in cash. Electronic circuit breakers becomes a big deal We're talking about 1000 amp or higher, or higher, or higher. So the one that we saw yesterday at Allianz, you guys remember that? That 4000 amp? Which one do you think? This has a thermal in it? These are electronic circuit breakers. They have sensors that sense the current in each phase, the neutral. It makes electronically circuit in it. It makes a decision that that current is higher than what my setting is, and it trips. Can I get you guys to understand the electronic circuit breakers? No fancy, other than contacts, they open based on a solenoid that energize from a signal that's coming out of the three-phase as well as the ground. Any question about this? Any question? So these are your circuit breakers, your electronics. So we have the thermomagnetic, 99% of the time, well, 80% of the time we're going to do thermomagnetic. Only when you start having 1000 amp or higher, it start making sense to have an electronic circuit breaker. I'll give you guys a break in a second here. When we have circuit breakers, I want you guys, you know that by now, every circuit breaker that you size with Chad is 1000 amp. This is called the trip rating. The trip rating, 1000 amp. And the interrupting rating for the circuit breaker is 65,000 amp. If you leave Dunwoody, not knowing these, call me for refund. I'm not kidding you. When you have a circuit breaker, there are two ratings for the circuit breaker. One is the interrupting rating, the trip rating, that's the overload. The other one is the short circuit. So this is basically, guys, the overload part, and this is the short circuit. Short circuit. What that means, guys, if I hit it, here's 1000 amp. If I have 2000 amp pulling out of this system, which one do you think is going to trip? The trip rating is going to trip. If I have a short circuit or a ground fault and I pulled 15,000 amp out of this, 15,000 amp, which one is going to take care of it? The trip rating. One component for the overload, one component for the trip, always. We're going to look at the curve in a second here, but please be aware of that one. So what do? If they have the trip, how do we size conductors? Anybody can tell me how do you size conductors? We size conductors based on this. Very important. Size conductors. Size conductors. Do we size conductors based on 65 kilo amp? Not really. Well, no. At this point, no. So that's your trip rating. Shunt, trip, and auxiliary contacts. Some circuit, now we're talking about electronic circuit breaker, guys. You know what they do with the electronic circuit breakers? They have, now we are acting like a contactor. Here's my circuit breaker contacts inside it. And they have, we're gonna sense I'm gonna put the sensors here, sense them. I'm gonna come to an electronic circuit. And this one, and I'm barely showing anything. This is all inside the circuit breaker, right? This is electronic circuit. They have the sensors. They sense, guys, that there's a current, trip the circuit. These are contacts. Close them or open them. These contacts will be closed or open. What they do with electronic circuit breakers or even thermomagnetic circuit breaker, guys, they have shunt trip. You know what they do? They have a little coil here that they can externally energize to trip the circuit breaker. So I can put 120 across this coil and trip the circuit breaker from my laptop. They call it shunt trip. When you went to the PDUs, remember that PDUs that we looked at yesterday? By code, requires a shunt trip on every main. So if there's a fire in that data center that you guys saw, remember that EPO emergency button off that looks something similar to this? If there's a fire in the building, the firefighters walks in, the first thing they do is they push that button. They push that button in. When they push the button, they put a 20 volt, 24 or 120 volt across the coil that's part of the circuit breaker of the PDU, and they bam, 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 trip all the circuit breakers of all the PDUs for safety. Another example of this, guys, if we use them a lot, shunt trip, they call them. It's nothing but a coil, comes with wires, wired, where you can bring a signal to the circuit breaker. It's like a magnetic starter. Do you remember the magnetic starters with Gary that we did? That's exactly like a magnetic starter. That's a shunt trip. The second thing that they do with them is they have contacts. 1, 2 auxiliary contacts. They have auxiliary contacts, guys, that they can come from these circuit breakers. So take this. If I want a light here to go on every time this circuit breaker, and I'm just exaggerating here, the way I'm look. If I want, when this is on, a light will say it will go on. Every time this circuit breaker is on, a light will go on. They have auxiliary contacts. They call them auxiliary contacts that comes with the circuit breaker that you can wire them to take a signal. Now we're starting to talk about control, exactly like that control on the wall. All of them, like a magnetic starter, remember with magnetic starters we did, all have auxiliary contacts so that you can take a signal in, out of the circuit breaker to interface it with other things. To summarize, I know you guys are not control engineers. When you get into the circuit breakers, they're more than just a dumb device in a panel like this. That's the lower level circuit breakers. These circuit breakers are up to the dumb ones that you talk about, they're up to 200 amps. Now these are dumb. They just turn on and off and they trip, thermomagnetic. You go higher than 200 amps or 3-phase 480, guys, and 225 amps. They start using them as a controller, almost as a controller. The circuit. As a matter of fact, medium voltage circuit breakers are used as a controller, Chris. When they turn a medium voltage motor on and off, you know what they do? They don't have a magnetic starter on the wall. They have a circuit breaker that you push a button, close it, now the motor is running, push a button, open it, the motor stops. The circuit breaker, no contact. So if you go to work somewhere else, Dustin, and they say shunt trip on the elevator, when we do fire alarm system, if there's a fire in this floor, it's supposed to send a signal to the elevator circuit breaker or controller and open and shut down the elevator, bring it to a certain level, shut it down. So that's how are you going to get a signal like this to interface through the shunt trip? Very, very important, the shunt trip business. Here's what and I'm going to give you a break in a second, guys. Here's what it looks like, guys. A coil. All these are built into the circuit breaker. You're not doing anything. These are all built into the circuit breakers. So if I have I need a thermostat. If the temperature in this room go higher than a certain value, say it goes 110, I want to make the circuit breaker in this panel trip. If the temperature in this room go 110 Fahrenheit, hot, I want to turn the power off because I don't want to create a fire, right? So you put a thermostat here, rate the thermostat 110 for tripping. When it hits 110, it brings a control voltage that could be 24 volt or 120 volt, any control voltage, external source of power. That's coming from somewhere else here. These are coming from somewhere else. Okay? So close it. Now you put 24 volt across this shunt trip. When you energize this one, this will push these contacts, guys. It will push them to open. Literally, physically, push these contacts to open. Shunt trip. Basically, interrupt the circuit. Any question about the shunt trip? You get out of here, you work in any industry, guys, you can hear the word shunt trip all the time. You're going to hear the word shunt trip all the time. What is shunt trip? Shunt trip when you bring an external signal to a circuit breaker to trip it. There's another term, William, that's called closing coil, or motorized circuit breakers. Motorized circuit breakers, you can bring a signal and actually turn the circuit breaker on. Turn it on, not off. Tripping it is easy. Turning it on, you need to have a motor that can wind it, especially big circuit breakers. When we went to EMI, remember how he was charging the circuit breakers when he closed them? You have to give him a couple of hits to charge them, and bam, it closes through a spring. Either you charge it manual through a spring, and then it closes, or you can actually energize a motor, and the motor charge the spring, charge the spring. When it has enough energy, it flips these contacts. Close. Shunt trip is remotely turning off a circuit breaker. Not a contactor, a circuit breaker. Auxiliary contacts, guys, that's really easy. you bring a 120 here, 120 volt, and here's my light, and here's my neutral. So every time the circuit breaker goes on, this will close. Guess what's going to happen to the light when this closes? The light goes on here. This light will go on. Now I have another light here. Here's another light, right? Coming from the same neutral. This light, every time the circuit breaker is on, this light will be, this will be off, this will be on, right? When the circuit breaker is on, this will close, this will go on. When the circuit breaker is on, this will open, and this will go off. Here's a physical indication. When you guys were walking around the switchgear, did you see this green and red light? You know, red lights on when the circuit breaker on, green on when the circuit breaker is off. That's how they do them. Contacts coming from the circuit breaker itself. And what they're not showing here, they're showing the other contacts for the 3 phases. These are for the 3 phases. And all this is inside a big fat circuit breaker. Any question about the auxiliary contacts? Okay, shall we have 5 minutes break, guys? And I'll talk a little bit about the molded case circuit breakers. Have to keep moving on that. Okay, back into the air circuit breakers, guys. Air. We're talking about the air circuit breakers as well as oil. They have just on time, guys. We haven't started. Sorry, bud. There are also 3 technologies that they build the circuit breaker from. Molded case circuit breaker. Remember that? That's molded case circuit breaker. That's an oil. No, I'm sorry. That's air. That's air circuit breaker, right? 99% of the time, air circuit breaker. And also low voltage power circuit breaker. It's called also air circuit breaker. These 2 are air circuit breakers. This guy is medium voltage circuit breaker. This could be air, could be oil, or could be vacuum. If I spelled that right. Okay? So these are 3 technologies. The way they split them this way is based on the structurally, how do they build them? Again, construction, based on the construction, how they build them. So molded case circuit breaker, Chris, you're looking at it right here. That's mostly thermomagnetic circuit breakers, like these. These guys, I believe they probably can 1600 amp max on these. These guys, power circuit breakers, they start making sense from 800 amp to 6000 amp. These babies, medium voltage circuit breakers, oh boy, these start making sense at 600 amp to 4000 amp. 4000 amp. See where it's making sense in terms of you're not going to buy a medium voltage circuit breaker for less than 600 amps. Good luck. You're not going to buy a low voltage power circuit breaker less than 800 amp. Now, yesterday, guys, at Allianz, did you see the drought circuit breakers? The drought circuit breakers that they were talking about? The drought circuit breakers are what they call the low voltage circuit breakers. Obviously, these 2 guys, voltage-wise, these 2 are 600 volt or less. These 2 are 600 volt or less, right? Low voltage. This baby here, right in here, the medium voltage, that's you're talking about 5K, 15K, 25K, and probably higher than that. These are higher voltage. Okay, so these are the 3 technologies. Why are they so important, Chris? Because of a nasty term that we use is called the arc. Every time you interrupt a current, do you know what an interrupting a current is, guys? I always told you, I don't know if I told you before. Imagine a semi, fully loaded, going down 494 at 90 miles an hour. Cool? 90 miles an hour. And you apply the brake. Can you imagine the amount of energy that you need to interrupt with this semi? You put your brakes on. Can you imagine how much energy you need to stop? That's exactly like interrupting a 65,000 amp. Or worse, that semi at 90,000 miles an hour, down the highway, it hits a concrete block. That's what a short circuit is. You have a 4,000 amp at 480, huge amount of energy coming to Dunwoody. And all of a sudden, you have a three-phase short circuit. It's exactly like that semi going 90 miles an hour down an interstate, and all of a sudden, it hits a concrete block, big concrete wall. Does that make sense in terms of the amount of energy that's going to be dissipated? Who cares? Imagine that big explosion that's going to come out of the semi. Exactly, big explosion is going to come out of inside the circuit breaker. It's called arc. Huge arc is going to come. And the longer the arc exists in the circuit breaker, the more you're going to damage the circuit breaker. So it's all about arc moving on forward. How do you extinguish the arc? Okay, here's my 4,000. Take this. Now here's my, this is a short circuit. I'm interrupting a short circuit, and the short circuit is 45,000 amp. I have a 45,000 amp coming to a machine. This is phase A, just phase A. And I'm opening the circuit breaker. So when you interrupt that 45,000 amps, huge amount of energy. Just to give you an idea how much energy, how much power, guys, take the 45K, multiply it by, at this time, let's just say 480, the voltage stays constant, multiply it by 1.73. I know the voltage will change when you have a ground fault. The voltage goes down. That'll give you how much energy power you're trying to interrupt here for a short amount of time. So this is usually within 3 cycles. 3 cycles is 3 over 60. That will give you 1/20th of a second. Within 1/20th of the second, you want to open the circuit breaker. So who cares? Guess what's going to happen as you interrupt it? There will be an arc. Do you guys remember Jacob's ladder that you did with Gary? Did you see Jacob's ladder? You've seen that? You didn't do it with Gary here? Or maybe not your group. You've seen it where you can energize it and an arc comes from, so let's just like this, an arc established here and it goes all the way up and dissipate. That's Jacob's ladder is what you want your electrical system not to behave. You want your electrical system not to behave like this. So that's similar to Jacob's ladder. When you interrupt, a huge amount of arc, guys, comes. The way you extinguish this arc will decide what type of circuit breaker you use. You extinguish it in oil circuit breaker, in air circuit breaker, in vacuum circuit breaker, and in air circuit breaker or vacuum, they have different technologies to extinguish this arc. Very, very big deal. That's a very destructive arc, guys. Very destructive arc. So remember, when you talk about, we're not here, guys, these circuit breakers, say 4,000 amp. The rating of this circuit breaker is a 4,000 amp. It's a huge amount of energy that you need to interrupt. Okay, so molded case circuit breakers, we talked about, guys, the voltages, typically 600. Low voltage circuit breakers make sense from 600, from 800 amps all the way to 6,000 amp. They make a 6,000 amp, but makes sense up to 4,000 amp. Motors, you can use them on motors or any on feeders, branch circuits, motors, lights, you name it. The way they extinguish the arc, guys, they have a splitter. I think I have a picture of it. And they split the arc to extinguish it. They have different technologies to break the arc and extinguish it. And also it permits the gas, when you have the explosion inside it, to interrupt it, to escape, but lengthens the arc so to dissipate and cooling effect increase. So they have technologies of extinguishing the arc and getting rid of all this energy inside it. You look at it when I show you a couple of things, guys. So low voltage circuit breakers, that's basically the molded case. Low voltage circuit breakers, you know what they do, guys? They have two separate sets of contacts, one for the arc and one for the circuit contacts, again, to extinguish the arc, and one set for the load and one set for the arc to extinguish the arc. This is how they build them. And then they put also arc horn, so moves the arc away from the contacts. The whole idea, guys, to move this huge arc away from the contacts, because you can burn the contacts. You want your circuit breaker to open and continue to open after the thermal event passes. So it moves away the arc from the contacts to protect them, and it stretches the arc so you can dissipate it. You'll look at a couple of pictures in a second here. So it's all about extinguishing the arc. It really is all about extinguishing the arc. Medium voltage, we talked about 15K here, guys, but you probably can go higher than that, and you can. So they have something called blowout coils. You're going to look at them in a second to distinguish the arc. So we'll look at the picture here, guys, in a second on these. The second one is the oil circuit breaker. Obviously, oil. What do you guys think? The oil to extinguish the arc. Full tank. They have a full tank technology or dead tank. Grounded the frame. The technologies that they have, these are high voltage. Here's the technologies: plain brake type, vented type, and double brake type. I'll show you a picture of these. Really, these are technologies of extinguishing this huge, magnificent arc that you're coming with. So I have a circuit breaker, guys, medium voltage circuit breaker. Let's say it's 1,000 amp circuit breaker, and let's say the voltage is 13.8 K, and I have a short circuit, and it's an oil. This is an oil circuit breaker. The contacts are inside the oil. So we'll look at these. Vacuum circuit breakers, we talked about vacuum. They take the tube, they get the air out of the tube, so you're not going to do any ionizing, and use mostly for high voltage, of course. Look at the clearances. This is my interest. The clearances between the contacts. Look, actually, you can get from half to 3/4 between the contacts. Who cares? It makes the vacuum tubes, guys, vacuum circuit breaker smaller in size than the oil circuit breaker. So they have advantage. Smaller sizes, a lot of advantage to it. You can put it in a tight locations. Little maintenance. And again, they always say it's not a perfect vacuum is not possible because there will still be a tiny little arc coming out of it, but it's much less than the other circuit breakers. And before I go to this, guys, let me just switch gear here quick and show you these technologies that we talked about directly into here, into library 13, and and then we'll go into the coordination very quick. Okay. Okay, we talked about the short circuit here, the ground fault sensors. We talked about. Oh, here's an interesting situation. For this one, guys, you see the bimetallic. This is just a bimetallic that trips right in here. Oops, I don't know if I can see that. My bimetallic, the moving contacts, the stationary contacts. My favorite is the arc shield. Can you guys see that little deal here? That's to extinguish your arc. To extinguish your arc. It's all about getting rid of that huge amount of energy. The arc shield in thermomagnetic circuit breakers. We talked about these technologies. This one here, arc shield. Can you guys see where the arc? I want to focus here. Here's a solenoid trip, blah blah blah. But I want to focus here on the arc shield. That's how with the arc, when you interrupt, the arc will be extinguished through these so-called arc shields. They develop it, guys, in the lab. They put all these devices and material there to, if they have an arc, I need to extinguish the arc so fast so I don't damage the contacts. Your goal, William, is two. Number one, move the arc away from the contacts so you don't burn them, the contacts that open. So when you open, you want the arc to move away from the contacts. Number two, you want to extinguish this arc as fast as you can and vent all this thermal effect, the gases and all the stuff outside. So move the arc away and stretch the arc so you can extinguish it and move the exhaust outside. All these are different technologies the manufacturers of building circuit breakers that they use to achieve the same thing. Move the arc away from the contacts, stretch it so you have enough time to open it and extinguish it and exhaust all this mess that happened inside your vacuum outside. Series coils, talked about these two. This is the thermal. We talked about this one. Shunt treb and auxiliary contact. This is a really nice picture, and you guys have all these. Shunt treb, here's your coil that comes and you're going to energize with 2 wires. And contacts here, you bring your contacts, 2 wires here to go to a light. Everything is built into one device. It's built into the device itself, as you can see. So wires coming out of the side of the device. We have one here in the lab, if you guys want to look at it. I brought it last quarter, I remember. So that's your shunt treb and auxiliary contacts. Here's your auxiliary contacts. We talked about this one, the arc. Okay, and the thermal I think this is a thermomagnetic. They call them splitters, guys. They use this technology. What they do is, can you see, they put these little splitters, and by doing it, they split the arc. It's all about getting rid of the arc. You can see that the arc now is split between these two sections. By putting this technology, the smarter than Chad discovered that they can extinguish the arc faster, better, and the goal is always to save these. Save contacts. Right? That's the whole idea. So see how they shifted the arc away from the contacts and they split the arc so they can control it and extinguish it. That's a technology that they use with thermomagnetic and others too.
So it's attracted to the plates.
You're moving it, I don't know the thermal effect, but they size them enough to put them in one section here, and that I'm not expert in extinguishing the arc, but that technology, splitting them into little chambers, basically help extinguishing the arc. That's all what we care about, unless you're going to be not really control here. This is the manufacturers. That would be a good question, guys, for the manufacturers when they come, manufacturer rep. How does these splitters control the arc? It splits it, I guess, divided into little segments that easily controllable to extinguish it. But you can see if it goes right through it here, it's cutting, right? You're cutting it here as it goes right through. So believe it or not, this technology saves your contacts. That's what we care about. Arc splitters, can you guys see where they put them here? They put the splitters in right here, so it can split the contacts. This is just FYI. Okay. Arc, horn devices, arc for, okay. The other technology, guys, in the medium voltage, I believe this is in the medium voltage, they use them, or even the low voltage, yeah, medium voltage, 23, as well as the low voltage. In the low voltage, look what they did. Now, the smarter than Chad, they have horns. Can you guys see their horns? You know what does this horn? This will channel the arc away from the contacts. Remember, what is the goal? What is the goal? The goal when you extinguish is to maintain this contact. This is save. The goal is save Private Ryan. Remember that movie? Save the contacts here. The goal is to save the contacts. So you channel the arc away from the contacts through these horns. You put them through the splitter so you can control them. And remember, this is an arc here. So you control them. In the vacuum, guys, this is your cylinder that you're going to interrupt. So look at the stationary contact. These are my arcing. And look at the arcing contacts. These are my arcing. So all the arc, I'm sorry, these are the arc. These are the one that's going to be arcing contacts. The contacts that you want to save mostly is these are the right contacts. I don't know if you guys can see these. These are the contacts that close and open. This is the stationary, and this one is the maintain. So the smarter than Chad decided to have two contacts. One set of contacts for the current to come in, go out. Here's the 4,000 amp, and here's out 4,000 amp. And when we interrupt, of course, here, and we interrupt right here, and we channel this is phase A, and we channel the arc away from the contacts that we're going to save. Save contacts. Anyway, so that's having two contacts, one for arc, one for the load, and also the splitter to extinguish the arc. So these are all about arc, guys. Same thing. Look what happened is when it opens. Can you guys see how it opens? It opens in two locations. So when it opens, I don't know if you guys can see that the current goes right in here, out. That's my arc current, and back. See how they move the arc away from, save the contacts. Save them. So they move the arc away from the contacts that we're going to save. And at the same time, there's also contacts. And also, they move them away from these. You don't want to burn these contacts. I guess you can replace these contacts. And through the arc horns, move them into the splitter. Long story short, it will save your circuit breakers. Guys, we are bringing a semi truck that's going at 90 miles an hour down 494 to a halt, a complete halt through a block concrete. That's what the amount of energy that you're interrupting here. So the whole idea is you want the circuit breaker to interrupt the energy and live to fight another life, another war, right? It's not just interrupted. Fuse will interrupt it and die. You guys the difference between circuit breakers and fuses? Circuit breakers, they 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 interrupt and they live to fight another war. Fuses, they die in the process of defending their territories, right? Which is good. Can we call them the kamikaze? Is that what they call them?
Yeah.
They're kamikaze, right? They die in the process defending their territories. Okay, moving into the medium voltage, this is called dead tank oil circuit. Now we elevated this one into oil. We're putting oil here. Anybody knows why we put oil? Now we interrupted in oil. Can you guys here's where my arc shoot here. Where's my contacts? There's actuator, operator, link. So now we have to monitor the air. Here's my arc contacts, my arcing contacts right in here. And main contacts, where's my main contacts? My main contacts are these contacts. I don't know if you guys can see. These are the contacts that the power is made. And the second one is arcing contacts. Same thing, arc contacts, main contacts, maintain the main contacts, arc contacts. Now you're arcing right in here, and you're arcing in oil. So the oil will fast extinguish the arc. Big technologies. And a couple of other things to adjust an actuator rod and so forth. You can lower them, adjust them, over travel adjustment. And from right in here, these are what you guys see. This is what you see, the 13.8K 1000 amp circuit breaker oil. You see them on the substations, the power coming in and out of the circuit breaker. Very few of you guys will be doing that, but the lucky ones will. I should bring one of them here. I assume it's going to be contact operator. It's going to fill at the most important thing. You need enough to fill this. I really don't know how much, but I assume most of it will be filled. For how long and how much they leave, there's a pressure, guys. When you get into oil, you get into pressure. You don't want to also make an explosion in the oil. So you have pressure relief and a bunch of other things. So the most important things is the contacts have to be completely immersed because you would explode it. Now, should it go up to this? I will leave it to the manufacturer. Or you can come next year. We'll give the answer for you. Okay. The other technology, guys. This is called. Plain break low oil type. Plain break low oil type. So this is another technology. Look at the stationary contacts here, guys. My stationary contacts, I will save. This is movable contacts. That's how you interrupt. You move it in. Again, I can't emphasize what's the word here, Mr. Oil. You interrupt different technology to interrupt with different oil for oil circuit breakers. This one has it's called typical vented type low oil. Vented type. Now this baby here, if you guys can see, it interrupts. Here's my oil. This is supposed to come in here to interrupt. So my circuit is coming in, I assume, and out. Here's my 1000 amp and 13K. These are high voltage, guys, all of them. Now, remember that whole venting issue you're going to create? When you interrupt, you're going to create heat and blah, blah, blah. All this will be vented out. Otherwise, if you increase the pressure inside this tank, what's going to happen to this tank? Explode. And I'm going to leave it like this. So that's why they call it vented. Because after the explosion inside it to interrupt the arc, it vents the energy out. This technology, guys, double break low oil. The smarter than Chad decided, now instead of breaking in one location, they break in two locations. So these will be, this is the place where you interrupt. Now when you interrupt in two locations, guys, what happens to the arc? The arc will split between two different, so smaller amount of arc, easier to extinguish it with the oil. Easier to extinguish it with the oil. And again, what do you guys see here? Vent. that huge energy have to be vented because you have thermal effect inside this tank. You got yourself a bomb. Okay, so that's where your power is for this type of technology. Now the best technology obviously is the vacuum. The vacuum is really easy. You get rid of every type of gas, and you bring your 13.8K 1000 amp right in here, movable contacts, stationary contacts. And Chris, where do you do the interruption? Right here's your contacts. Now, very, very minimum amount of arc. Who cares? You don't have to go change the contacts every time you have a short circuit or you have an overload condition. Cool. And you have to seal that chamber. This is a cylinder, vacuum insulated cylinder. So you have to seal it and do all the sealing for the vacuum, blah, 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 and so forth. So what you're doing is you're interrupting inside the cylinder, a vacuum cylinder, vacuum chamber. The whole chamber inside the cylinder is where you interrupt. Everybody knows why? No air, no ionization of the air, no arc. That would be nice to wire the space then. If you don't have air, you can interrupt the arc. You don't have to do any, even vacuum. I don't know. Probably they have someone else. Okay, so that's guys where I'm gonna switch track. Any question about these technologies? The technologies know them as, you know, FYI. It's a good chapter, as I said, to read. But what I'm going to focus a little bit here is on the overcurrent protection device. Now, when we move later on, guys, we're going to do circuit breaker time current characteristic curve. You have to, with your friend Chad, understand this curve, guys. As we move on, I'll highlight one and we'll look at this particular one. This is called, if you are an engineering firm or a major electrical contractor firm, you're going to hear this all the time. It's called time. So this is your time right here. Current. This is your current. Characteristic chart or curve. They call it curve. And here's your curve. This is the faster, the higher the amp, the faster it trips. The higher the amp this way, the faster it will trip. The system will trip. We'll look at this example in a second. You have to understand every circuit breaker or fuse or ground fault has a curve like this. So that's called time current characteristic curve. Today, guys, a software SKM I downloaded in your machine. That's what you're going to be looking at. If you don't understand what this curve is, good luck doing the coordination. You have no idea what the coordination is. This coordination, guys, will transfer into a data that you give to the electrician with a nice screwdriver to go to the face of the electrician and set the face of the electrician, face of the circuit breakers, and set the circuit breakers at the right settings. That's what this translates to. Big deal in the high voltage. Okay, I'll talk about this one, guys, when we reach it. The fuse, the same thing, guys. Fuse also have its own time characteristic curve. Ground fault, Chris, believe it or not, the ground fault also have its own time characteristic curves at different values. We'll look at this in a second. All these have time characteristic curve. Coordination, guys. So that's, each one of them has a curve. Now your coordination is to make sure that these curves don't touch when you put them. Here's what the coordination is. Here's curve 1, curve 2, curve 3. So this is curve 1, curve 2, and curve 3, right? This is what coordination is. This one is going to be, we'll look at this one. This is a 4,000 amp, 2,000 amp, 1,000 amp. These are fully coordinated curves, and the field that we're in is right in here. And I'm just minimizing this. So coordination is to make sure the circuit breaker closest to the fault will trip. So you guys will do it with me. You have to tweak the circuit breakers, find the impedance. So it's a big deal. So let me switch into a couple of curves I'm going to show you guys, and then about the coordination. Okay, so if you guys look at this is you must be able to understand this one. The most important, this one, guys, is is this value here. This is 1000 amp. 1000 amp. This is called long time pick up. That's how you size. This is how you size the conductors. That value is how you size the conductors. That's how you size the conductors. Maximum clearing time. So this is a ground fault. Can you guys see right here? If you have a ground fault right in here, that's an overload condition. You went from 1000 amp, Chris, into a 2500 amp. That's an overload condition. You will trip within these 2 points, right here or right here. Okay? Between these 2 points, that's the amount of time that will take you to trip. In this case, it's 110 seconds. It will take you 110 seconds to trip if you double the amount of current on a 1000 amp. Very, very important to be able to read this. So what they're saying, guys, minimum clearing time is 23, minimum clearing time, and this one is maximum clearing time is 120 amps, 110 seconds, the maximum, and the amount that in between them is the amount that takes you to between the time. This is the time between the time the circuit breaker will sense that there's short circuit to completely open. See that little time here, confusing all the time. This little time here is the time that we think the circuit breaker, since there's a short circuit, opened. So if you do the math between this, Chris, if we do the math here, so 110 minus 23, so 10.7, that will be 10.8, right? Did I do it right? 10. So we'll take 87 seconds for this circuit breakers. Within 87 seconds, the circuit breaker will interrupt the circuit. Within, from the time it says.
You're reading the 2500 on the bottom of that chart. You had current on the x-axis.
Yep, it's right here. The current was right here.
According to the chart, it says 60 times 100.
Did you multiply by 100?
Okay.
Right here, it's times 100.
Okay. So
Yep.
6,000 amps at the very bottom of that curve.
At the bottom here? Yeah. Whatever that number, I can't see it. Yep. Yep. No, it's set 300. 3 times 1,000, that will be 30,000. This bottom point here, if we're looking at the same curve, that will be 30 grand, 30,000 amp.
Yeah, I was looking at it.
30,000 amp. Okay, it's very important, guys, to understand this one when we do the coordination. And again, I'm going to do it tomorrow. The whole coordination is. So that's basically your overload condition. This one here is called your overload condition. Your overload condition. Long time delay. That's a delay that they allow you. A long time delay. We'll look at this. Instantaneous. 7 times the trip settings. 7 times the trip settings. So 7 times, first 7 times 1,000 is what? That will give you 7,000. 7,000 amp. At 7,000 amp, this boy is going to go nuts and going to trip instantaneously. It's going to trip instantaneously within that amount of current, within 3 cycles. This value here, guys, is the largest amount of current that this circuit breaker can interrupt. So in this case, this circuit breaker is rated for 30,000 amp. 30,000 amp. Any comments, any questions? Tomorrow, guys, or Friday, we will be dropping these. We will be putting them together for our system. The 4,000 amp switchgear that we did, you're going to pick up a circuit breaker from collar hammer, grab it. It will come with a curve like this and coordinate that curve. Coordinate that curve. So that's the coordination for this breaker. Okay. Now this part, guys, is called the instantaneous short time delay. Short time delay. I don't know if you guys can see this one here. If you move it here, this is 30 cycles. 30 cycle delay, meaning 30 cycle is 30 divided by 60 equal half a second. That's eternity. So if you drop it down and give the value to the electrician, that's 6 cycles, Chris. So 6 divided by 60, that will give me 1/10 of a second. So I can adjust the instantaneous. What does that mean? It's telling the it's telling me, guys, if I have a short circuit right here at this value, let's just say this value is 700, so 70,000 right here. If I have 70,000 amp, right? If you go to the bottom of it, 700 plus 2 zeros, right? Times 100. Yeah. Yeah, so that will give you 70,000. At 70,000, Chris, at this time, it will take me 1/10 of a second to trip. Or I can move it up. It will take me half a second to trip. Very, very important, guys, to understand the coordination. Who cares? You're going to give this value to your electricians and go adjust the circuit breakers that we were talking about yesterday. We were looking at.
So in that particular case, that breaker would have to be rated at over 70,000.
Yes, thank you. 70,000 or higher. Otherwise, it's going to blow up. Yep. This circuit breaker here, I'm assuming it's going to be an 85 kilo amp circuit breaker or higher, or 70 at least or higher. So that's your instantaneous. This is really cool, guys. Look at this. This is when you have a circuit breaker. This point is when the circuit breaker see. This point is when the circuit breaker see that I have a short circuit. This point here is when the circuit breaker completely interrupts the circuit. And in between them, press how many cycles? 3 cycles. So 3 cycles divided by 60 equal 1/20th of a second. Almost all circuit breakers, guys, are rated to handle 3 cycles. So 1, 2, 3 cycles have to interrupt the short circuit. If you don't interrupt the short circuit within 3 cycles, guess what's going to happen? Your circuit breaker will be charted, completely burned. So that's what they call it, the opening time. From unlatching, start the process of opening, into the completely open, takes you 3 cycles. Their circuit breakers can open in a quarter of a cycle, guys, half a cycle. Almost all the overcurrent protection devices are rated to open 3 cycles or less. There are other circuit breakers that are rated for 30 cycles for coordination. So within 3 cycles, believe it or not, you're going to interrupt the circuit. If you have a Mr. Fuse, Chris, Mr. Fuse, the same thing. I'm going to highlight this right here, guys. Right here and right here. This is the time that it takes for the fuse to burn. If you have a ground fault or short circuit value. So total clearing time is 120 seconds at 200 amps. And what size is this fuse? This fuse is so minimum clearing time. So here's my clearing time. This is my minimum clearing time. It's 25. You can do your math between how long will it take you. Between 120 minus 25, that will give me 5, 11, 9, 95 seconds. It will take between the time we sense to the time we open. This point here, if you have a short circuit higher than this point, Chris, you get yourself a big ball of fire. This area, this is the area that's protected. Anything to the right of the fuse or the circuit breaker is what's protected. This area is called protected. Protected. Now, Alaribo, what happened to this area here? This is not protected here. Not protected. This is not protected. Not protected. Very, very important, guys, the time current characteristic curve. I'm going to show you a few things here, and we're almost done. Okay, let's go here. We talked about the ground fault, guys. Your ground fault here, you can set the ground fault, Chris, at 0.5 seconds or 0.1 seconds. By setting it at 0.5 seconds, you allow the ground fault to sit longer in your system. Right? By setting it, when you give the electrician these settings, they go and tweak the face of the circuit breaker to adjust to 0.5 seconds or 0.15 seconds. You know who cares? If you have an arc, inside your switchgear. It's a function of how long this short circuit or ground fault is going to sit in your switchgear. So that will decide the PPE, personal protective equipment or gear that you're supposed to put on yourself when you work on energized equipment. So that's a big deal. Big deal for us. Okay, come on. My computer went into a coma. And the last couple of ones, guys, is just over-competition coordination I'm going to show you. So starting today, when I load your system, guys, with the software, I want you to review, and if you have not read this chapter, please do so. If you want to understand this system, if you want to stay in this field, and that will be one niche that you can make good money out of doing the coordination. Okay, here you go. We're there. Okay, so now moving into the coordination. Now every circuit breaker guys have a coordination curve. I want you to look at this, please. I have a 600 amp. This is my 1600 amp circuit breaker. This is my 800 amp circuit breaker. This is the 800 amp, and this one is a 16, right? Can you guys see where curve A and curve B is? These are fully coordinated, except Chris. Coordinated means they don't touch each other for the most part. So anybody can tell me, where do I have a problem with the coordination just by looking at them? Well, Chad, right here, right? Can you guys see this area here? This area is not coordinated. So what does that mean, Chris? If I have a short circuit in this area at this level, so if I have a short circuit right here, and the short circuit was at this level, I really don't know which one of them would trip. Both of them will trip. They're not going to coordinate. Another area that they're not coordinating here, can you guys see that right in here? That little overlap area? The overlap area, Chris and Ashley, can you guys see that little overlap? Every time the overlap, this means if you have a short circuit right at this level, I have miscoordination. What does that mean? You have a short circuit in this light, it will trip the main at Dunwoody. Now you'll find a lot of people yelling at you if you're an electrician or an engineer that you have done a system like this. I can't emphasize, when you have over-competition coordination, guys, when I show you the software, when we download the software, your goal is not to overlap these curves. What does that mean, overlapping them? Not overlapping them means they're set at a different values. Any question, guys? So I want you to understand, you look at this just by looking, overlapping, miscoordination. Overlapping, miscoordination. Can you guys see where they are coordinated, Chris? Can you see where the coordination is? They're fully coordinated in this area here. Perfect. See that area here? And here, can you guys see where they're fully coordinated in this area here? Right? So I have the green is coordinated, fully coordinated. Right, these two, this is no coordination. Right, in these two areas, no coordination. So if you guys have a circuit breaker that sometimes it coordinates, sometimes it doesn't, well, it depends upon the amount of short circuit in the system. If the short circuit is within these red area, it's not going to coordinate. If it's within this blue area, it will coordinate. So that's that's coordination. Let's go to a fully coordinated system here in a second. Take this. This is what you want to see, guys. When you do coordination with Chad, that's exactly what you're going to see. What you would love to see. Can I get you guys to understand that this is, these are 3 circuit breakers. I'm going to highlight the first one with red here. This is my circuit breaker here. So here's my main circuit breaker right in here. You guys can see that's fully coordinated. And then I have my B, which is my second circuit breaker here, right? All the way fully coordinated right here. So this is my B right in here, my circuit breaker B. And this is my circuit breaker A. And the last one is the branch circuit C. The branch circuit is that baby here and completely coordinated. Can you guys see that all the way? This is what you're going to see tomorrow when we do SKM. You're going to see literally color-coded curves like this. They don't overlap, fully coordinated. They overlap, they don't coordinate. They don't coordinate. Any question, guys? And the values, this guy is 100 amp. This one is 100 amp. This one is 300 amp. 300 amp. This baby is 20 amps. 20 amps is right above Ashley. There's a light. If there's a short circuit right there, the circuit breaker 20 amp here will trip. For whatever reason, if it didn't trip because of malfunction, then the big boy, the 100 amp for the panel will trip. If that also malfunctions, so this is line of defense 1, line of defense 2, line of defense 3. But for Pete's sake, you really want line of defense 1 to take care of business if you don't want people to yell at you. You don't want to trip the main. This is the branch circuit, the feeder, the main. Do you want the main to trip? No. Can you guys give me a thumbs up and see, Chad, if you look at a curves like this, we know it's fully coordinated, right? It's not rocket science. You look at them, are they overlapping? No, fully coordinated. Are they overlapping? Yes, not coordinated. You're gonna see that these will translate into settings. This will translate into settings. They call it long time pick up, long time delay, short time pick up, short time delay, instantaneous. So these are the ones they're going to send to Mr. Electrician. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? So 5 things. So you're going to go to Mr. Electrician. You guys are given these numbers. Number 1, long time pickup. I'm going to set it at 0.9. So you're going to go with a screwdriver and set 0.9, right? From 0.1 to 1. Long time delay. I want to set it at say 5 seconds. Short time pickup. I want to set it at 20.
Where are you getting these numbers from?
You're going to see later on when you look at these are
Oh,
comes.
you're not taking them off.
No. These have nothing to do with this. Yeah. Short time delay, I'm going to put it at 10 seconds. Instantaneous at 25. These numbers, guys, come with the circuit breakers. I want to show you in a second. Every circuit breaker comes with these settings. They're all called long time pickup. These are electronic circuit breakers. Long time pickup, long time delay, short time pickup, short time delay, instantaneous. Instantaneous.
They seem to go backwards. The long time is the shortest interval you have there. The short time is the
They,
longest.
don't look at the time though. These are the time is a different.
Write it down.
Yeah, is a different, really different, different function. So, and I'm throwing all these. This is 5. Yeah, they're different values. So don't look at the exact time. I'll give you guys an exact time for an exact example, but I want you to understand long time pickup, long time delay, short time pickup, short time delay, instantaneous. We will do an exercise on sizing based on these. So I just want to introduce them. I'll get into them in details as we get into the motor. I just start to write them here. You can do coordination between a fuse and a circuit breaker, Ashley. Here's your circuit breaker here. Here's your fuse. Are they fully coordinated? Yep, they're fully coordinated. Right? They're not overlapping. So they're fully coordinated. You can also do, this is interesting. You can do 2 coordination, guys. Coordination between the ground fault. This is a ground fault. Remember that ground fault protection? Ground fault. And the other ground fault, they are fully coordinated. So these 2 ground faults are fully coordinated. And also you have the fuse. You have my fuse here. I don't know if you guys can see the fuse coming in here. And also the circuit breaker, which is coming right in here. Coming right here. This is my circuit breaker. So, can you guys see that there's fully coordination between 2 things here? This is for the 3-phase. This one, 3-phase short circuit. And also this one is for 3-phase short circuit. The ground fault is this one. This one for ground fault, and also this one for ground fault. So, Alaribo, do you see that blue is crossing the blue? Is that okay? Yeah, no problem. They're two different things. The ground fault has to coordinate with the ground fault, and the three-phase have to coordinate with the three-phase short circuit. Cool? But the three-phase, like this one, see that red is crossing that blue? That's okay, because that one is a ground fault and that's three-phase. They're two different things. Can I get you guys, by looking at this, to understand this? In this graphic, there are two coordinated curves. One of them is for the three-phase, which is this one with this one, and the second one is for the ground fault, which is this one with this one. These two. Ground with ground, three-phase with three-phase, done. You don't have to do ground with three-phase at this point.
Why is there a difference between the ground fault lines and then the short circuit golf pumps?
Because the ground fault looks at line to ground, very small amount current, versus the three-phase looking at line to line, phase to phase, or phase to phase to phase, a higher amp setting. So different settings. The ground fault is almost always, the ground fault is lower than the three-phase short circuit. That's why they are at different values. They're always at different values. One of them, it's two different things here, guys. One of them is looking at ground fault only. The other one is looking at three-phase short circuit or phase-to-phase. When we get into coordination, guys, you're gonna basically looking at these curves exactly like color curves when we do the SKM. It will be clearer as you go through with the SKM. Now, all what you're looking at here is meaningless when you give it to an electrician who is not familiar with this. You're going to translate this into a piece of paper, an Excel sheet. An Excel sheet is going to give you the values that we talked about, guys. Long time pickup, long time delay, short time pickup, short time delay, instantaneous, and ground fault pickup and ground fault delay. Give them these, 7 values. Literally 7 different values. They're going to walk into the face of the circuit breakers with a screwdriver and adjust these settings on the circuit breaker. Done. Most of the electrician has no clue what they mean, right? Why did I give you 5, not 25? You asked me, why did you get 5? I just throw it out of the window. But if I am doing a coordination, I tell you exactly what I did 5. So that's very, very important, guys, to understand this. And I know it's a topic. And then the rest of them just talk about all these, really not a whole lot. Okay, so that's my favorite. I know you guys, you're going to be patient with me. I really want to show you one little thing here, color hammer. I told you guys to grab color hammer book. And I want you to do me a favor. Could you please go to, this information should be from color hammer circuit breakers. This should be section 26. Can you guys go to section 26 in the book that you have, please? Section 26. Section 26. When you guys go to section 26, it says Magnum product. They have DS low voltage. I don't know if you guys can see it. There's these are power circuit breakers. They are power circuit breakers and insulated case circuit breakers. Insulated case circuit breakers. These are what we're just talking about. Power circuit breakers is a power circuit breakers. It's the draw circuit breakers. Insulated, they're kind of in between. So low voltage. So this talks about power circuit breakers, the most important things that we're gonna. When I told you guys you're gonna have a cut sheet about the switchgear for the project, where are you gonna go? Right here to Magnum power circuit breakers. In particular, I want to show you how they rate them. If you have never been there, just because here's how they look like. You guys have seen yesterday when we went to. They are big, probably a foot by a foot by a foot circuit breakers. That's how the physical size of them. $20,000 each. Here's all the function that comes with them if you want to read more. But I'm going to take you in particular to, here's how Chris, I want to highlight this in particular. When you give the electricians, can you guys see that curve right here? here, 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 and here. Anybody paid attention to this yesterday? Can you guys see the settings that are coming out of it? That's where Mr. Electrician is going to go sit this one, sit this one, sit this one. So this will be long time pickup. I believe this is long time delay, short time pickup, and long time pickup, short time, and it should be a short time delay here, somewhere here. This will be instantaneous. Instantaneous. Am I missing something? Yeah. This one. There's one more here. Short time right here. Short time delay. And for the ground fault, pick up and ground fault delay. These two values. Long story short, guys, in the face of the circuit breaker with a screwdriver, you're going to go right there and adjust the circuit breakers. Done. All these, how many settings, Chris? 1, 2, 3, 4, 5, 6, 7, right? 1, 2, 3, 4, 5, 6. Six settings that you have to set on the circuit breakers. That's exactly what you saw yesterday, guys, when we were at Allianz, the 3000 amp circuit breaker. Okay, so I thought just to get you to look at this on that one. So these are real equipment in the field, guys. Here's where you can adjust them electronically too. So it talks about hold the adjustment for it and all this stuff. I'm going to take you to page 10, and feel free to look at those information just to learn more about them, guys. I'm just going to take you to page 10, the sizes. There you go. Now, I want you guys, oops, no, page 10, Chad. Go to page 10. Okay, page 10, this should be page 10, no? 26.1-7, I'm sorry, 26.1-7 for you. 26.1-7. This is Magnum switchgear class UL circuit breakers, low voltage power circuit breakers. I want you guys to look at how they rate them, really cool. Look at, you can't buy anything less than an 800 amp. Look how they start with an 800 amp. This is called the frame size, the frame amp. 1200, 1600, 2000, and underneath it they go higher. So I can't emphasize, these guys here are called frame size. This means how big physically the circuit breaker is. Doesn't mean anything. Right in here actually is what matters. This is called the plug size rating for these trip unit. This they call it trip unit size. So Chris, take this. I have a circuit breaker. The frame size is 800. Trip size is 200. Amp. Can you guys see now we're going into different things? Trip size. The frame size 800, trip size 800. How are you going to size the circuit breaker? The cable. Which number are you going to use to size the cable? The trip size. On the face of this circuit breaker, guys, they have a unit that you can plug it into the face of the circuit breaker. That trip, you can have, you can make the 800 amp 200, or you can make it 250 or 300 or 400 or 600 or 800, based on the literal electronic equipment that you plug into the circuit breaker. It gets more interesting then. Then also sitting, trip sitting, the trip sitting, I'm going to sit this one at, excuse me, at 0.5, Chris. If I sit at 0.5, what's 0.5 of 200? What's 0.5 of 200? 100. This circuit breaker right now is a 100 amp circuit breaker. I took an 800 amp frame circuit breaker, I made it 100 amp. So Ashley, you're going to pull 100 amp circuit cable to tie it to this circuit breaker. Very, very important, guys. Power circuit breaker has 3 very important values. 1, it's called the frame. This is just how big the circuit breaker is. 2 is the trip. This is a 2. This is a 1. Right? 2 is the trip. This is the electronic piece that come in the face of the circuit breaker. Adjustable. You can plug one and unplug another one. And the third one is the sitting. Remember that long time pickup and long time pickup? This particular value is long time pickup. The long time pickup value.
Where are you getting that from? On that piece of paper?
This is from the curve. Every circuit breaker will have a curve. Yep. Every circuit breaker will have a long time pickup. And I put that long time pickup, Chris, they always go from almost 0.1 to 1, right? And I picked 0.5. You'll see it, guys, when we start doing the coordination. Okay, so that's basically all how they do the power circuit breakers, low voltage power circuit breakers. That's what you were looking at yesterday when we went to Allianz. I will bring to your attention, guys, very important thing. It's also the interrupting short circuit, interrupting values. Look at these in thousands of amps. Okay. Any comments, guys? Any questions?
What's with the weird voltage?
This is 5060 interrupting at 254 VA, interrupting at 508 VA, interrupting at 635 VA.
Is that full AC or is it?
This is an AC voltage.
Do you have any idea why they use those numbers?
I don't know what. It's a good question. Or lower. This is or lower. These are 600 amp. So interrupting is 635, 254 at okay. They have different the short circuit withstand rating. The withstand rating, they're almost the same. The most important value. This is interrupting a different voltage, of course, without getting into the most important values you want is the withstand value and the interrupting value of the devices here at the almost the rated voltage. The voltage is what, 600? At the rated voltage close to 600, it can give you these values. Okay, so that's I wanted to show you guys this one. Now, this goes all the way to 6,000 amp, guys, as you can see. 6,000 amps, all the curves for them, you name it. Tons and tons of information that you can get about these. All these curves that come with that baby. And I'm going to spare you the sensors, sizes, and all this good stuff. Ethernet, you can, at this level, guys, you can get your circuit breakers to be an electronic circuit breakers controller. You can Ethernet, pick information from, go to. Okay, I don't know if I showed you guys this. This is Eaton Cutler Hammer Consulting Application Guide. This is the electronic version of what you're looking in front of you. You can go there. I can email you this link. You can go everything that you're looking at. You can find it electronically there. The last thing I'm going to show you is molded case circuit breaker 27. So if you guys go to 27, and then I'm done. At 27, I promise this time. If you guys go to section 27, open section 27. This is all the molded case circuit breakers that Eaton does. Can you guys see how they look exactly like the ones that you're familiar with? I'm sure you are familiar with, well, some of you anyway, familiar with this circuit breakers, right? These are your molded circuit. These are bolted on circuit breakers. You bolt them to the switch gear. Here's all the rating that you can come up with, the voltage rating and so forth. I want to go into the trip units. Can't remember which page. I can find it here. The sizes that you can get them at. So there's tons of information, guys, about these equipments. It's a whole different animal. You can here you go. If you guys look at this, these are 1, 2, 3, 4, 5, 6, 7, 8. 8 electronic digitrip, they call them. Electronic trip units that you can actually install in a molded case circuit breaker. Obviously, the higher the number, the more functions you can get. And I'm going to spare you the hassle of getting into it. But I want you to look at Rob. Can you see each one of them has this curve in front of it? Does it sound familiar? You see this curve that keeps repeating itself? and this tiny little curve next to it, the tiny little curve is always ground fault, the big curve is the three-phase short circuit. Pickup and delay. How long you will allow the ground fault to set, and how big the value of the ground fault before it trips. Two values. So here you go. This is what I wanted to show you guys. Please go to, this is which page this is, Chris? It's 27.15. For those of you who are doubting Thomas, and they were saying, Chad, where the heck did you get up the pickup, delay, and all this good stuff? Please go there and write the following. Right next to this one, long time pick up. This piece here, long time delay. This piece here is short time pick up. This piece here is short time delay. This piece here is instantaneous. And this piece here is ground fault pick up. This piece here is ground fault delay. If you do me a favor, write on this one, and you can read about them, tons of information there. If you understand this, when I walk you tomorrow or Friday, guys, through SKM, you're going to say piece of cake, Chad. Piece of cake. Can you guys see the arrows here? The arrows indicate that you can adjust this way, less, this way, more. Less, more, less, more. To the right and the top is always more. To the right or to the top is always more. To the left or to the bottom is always less. Always less. And you can read about the instantaneous right here and how they size it. This is very, very important piece, guys, that comes explain the setup for circuit breaker. Now, these are only for electronic circuit breakers. If it's thermomagnetic circuit breaker, Chris, you barely can. If it's a thermomagnetic circuit breaker, guys, it will look something ugly like this. And sometimes they have adjustment on the instantaneous. Sometimes they only have pickup. Long time pick up. If it's a thermomagnetic, the adjustment on the thermomagnetic is very limited. Very limited. Sometimes
long. They're using the book fairly standard.
Yes.
Long delay, short
Yes. Yes. When you go to SKM, the software that we use, they're going to be using the same. You're going to see LTP, LTPU, LTD, STPU, and all these terminologies. Long time pickup, short time pickup. SKM almost use these terminologies. So you need to be able. And oh, by the way, guys, next week we're going to be sizing circuit breakers based on these. So you're going to go and size them with Chad. So it's you're going to see them a lot next week. Okay, so that's your circuit breaker setup. A nice picture, I thought, from Cutler Hammer. Here's the coordination and all this good stuff, zone coordination and blah, 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 all this stuff. You can read tons and tons of information. All the trip units, guys, that we were talking about. Chris, you were talking about the interrupting rating. Here's a nice molded case. These are a molded case circuit breaker, short circuit rating at 60 hertz only. That's us. And here's all the type. These are the frame type. Here's the amps. And here's the short circuit at different voltages. Now we're talking about our language, right? Our system is 480, so we're going to be right in here. When you guys do the short circuit calculation with your friend Chad, you don't see a 4,000 amp here, right? That's because they don't make him at 4,000 amp. You go to the power circuit breakers. So suppose that you have 2,000 amp molded case circuit breakers. The interrupting rating is going to be a 65,000 amp. You can buy them up to 65,000 amp. Who cares? The higher the interrupting rating, the more expensive the equipment will be at different voltages. So please highlight this one for you. I thought that's I can't emphasize, and again, I'm not bought in Cutler Hammer, guys. This manual, as a consulting engineers, and most of you will be working in engineering firms, this has to be on your desk. If you don't have one, make sure you have one. And if you are like Chad, make sure you have the electronic copy with you. You can size, you can educate yourself about tons of, not just the book that Chris keeps complaining about, Chad's book here, about real-time equipment in the field. That's what we specify. They update it yearly or so. So it's really cool stuff. And you dip into it as much as you need. Okay, so that's more information, guys, about the circuit breakers and so forth. I thought to show you, they go even into the physical dimensions, so you can size and how to size it, how to order them, how to order the frame circuit breakers, the Kellogg number, and tons of information. This is where Todd Christensen, the guy who came here, guys, come very handy. If you read something you don't understand in this manual, what do? You call the manufacturer. Don't call your friend Chad. You can. I might give you a wrong answer. But something really deep into the manufacturers, you call the rep and they will explain it to you. Cool? Okay, so that's basically what I wanted to show you guys. A couple of things about circuit breakers. I think we are good with the circuit breakers now. I think. So what I'm going to do, guys, tomorrow, I will, and today I'm going to upload your software SKM. I will walk you through how to build the system, the one-line diagram into SKM, and how to run short circuit calculation. Any question for Chad, guys? Again, more to come about the topic of coordination. More to come. So it's not the end of it.